Okay, we're at the top of the hour. I'm going to get started on today's presentation, be about an hour. I'm a picture guy. My next slide's kind of an intro slide. My name is Tom Daugherty, but I'll have an intro slide coming up. But I'm going to show pictures of a blower fire, talk about a job where we're medium permit with one lagoon cell offline, maintaining pressure in an aeration system with a tapered lagoon bottom, rolling open, other field observations. So just a little bit about me. I like to, when I'm sit down one-on-one with a guy, get some background on somebody, but just to give you a bit on me, Tom Daugherty, as I said, Western Region Manager for Triple Point. Outside of Triple Point, I'm a licensed bond and insured general contractor. I'm a licensed wastewater operator. And I mentioned this next bullet. I built a Silverwood theme park in Idaho some 16 years ago because it's kind of relevant to some of my experiences. That was from permitting to get it approved from DEQ to design with engineers to getting it built and opened up, and then we contract operated it for 3 years. And so it was pretty much an alpha omega experience in the wastewater space. I have a somewhat eclectic background with an MBA, being a wastewater operator, but I'm kind of a millwright skill set and can also keep track of stuff in a spreadsheet. I do teach a business class, evening class at Gonzaga. It's been off because of COVID, but we'll do that again here starting in August. So just a little bit about my background. I just turned 62 a while back, so I might be a little bit salty at times. But this picture on the left was back in 2014, by the way. That's a frack water pond. And you can see in the foreground here these beakers of this is the frack water and then clear water on the side to look at the differential. And I've got a sludge judge there. I was doing some work at some aeration to try to clean up some frack flowback water. So I'm going to jump right into the blower fire anatomy of a blower fire. I could call this a blower fire background. So this was occurred at a 20 million gallon pond filled in January 2021. It's a new construction. 200 horsepower blowers, you know, a lot of SCFM each. There was 152 of Triple Point's aerators there, 2 separate control panels with VFDs. The blowers were staggered because a COVID issue shut down Gardner Denver line somewhere in the country, and so they couldn't get them there both at the same time. So they staggered. That becomes somewhat important on this fire situation. Anyway, the blowers run in parallel from 50% to 100% pool fill. This pool goes up and down all the time. So we intentionally did dual blowers in case there was a catastrophic failure. And one blower will actually do pretty good diffusion patterns in the entire pond. And our design criteria was to take 12,000 COD down to 1,000 COD. This was a sugar beet processor. So just this overhead site view of this sugar beet processor in Idaho. A lot of ponds all over the place. The pond we were working with is right here. And just a quick look at the control panel we put in there. We always have an external hour meter so that you can find that through the VFD HMI. But we like to have a separate one right there that just the operator can walk up and look at what the hours are, and on button, off button. And a potentiometer is nothing more than a way to adjust the VFD, just turning a knob versus holding your finger on a button. It's just typical control panel configuration. So these 200 horsepower blowers, this particular vendor was Universal Blower Pack, and you lift off the entire panel and then set the blower, and you put the enclosure, I should say, versus panel back over the top of it. So it's a pick, and then you set it on a site pad. So this is what it looked like finally installed. This is the below grade, where it's actually at grade almost with the bottom of the lagoon. So here's the exterior of the bank going up and over, air going up and over, 2 separate control panels. So blower fire. This was the second blower that came in. And this is 8 belts, and it's only 355 hours on the meter. We'd already started the plant up and been going forward and just operating with one blower until the second blower got there. I wasn't there for the startup of the blower. I did go down and help put oil in it. These arrived without oil. But it didn't have electricity. There was an issue with the local utility company, so it kind of was not much accomplished on the trip other than putting oil in it. 355 hours later is, a couple weeks or less, and this is what we got. And so the site environmental manager called and said, we had a blower fire, and that's what the belts look like. And this particular sheave size and these 8 belts is going to be important as I show additional pictures and talk about what the remedy was, what caused it, and what we did to remedy it. It's another smoke coming out the top from the insulation on the inside of the blower. Was melted. Literally just gets hot and melts. I don't know that there was particularly flame in there. There may have been, there may have not been, or just intense heat, but enough heat to cause this sort of damage inside to the enclosure. Just melted and dropped down. So what we were able to determine, though, that was somewhat superficial damage. It was just heat. It heated things up, but it did not integrally impede the operation of the blower itself nor the motor over here. They still freely turned. So when the first response was, is the fire the heat out? They call up on the phone, and we're trying to manage this situation from afar. Yeah, blower components are cool to touch. We believe it happened on the weekend, found it on a Monday. Large site with their own maintenance people. They have a lot of VFDs, blowers, belt-driven equipment from motors there. So they had a maintenance staff over, verify the blower and motor spin freely, check oil level in the blower. And we told them to pull a sample for a visual and lab testing, only concerned if it got so hot that the properties had changed somehow. It was determined that the oil was fine. They had spare belts on hand, and so we counseled over the phone to realign and tension the belts, and the site maintenance used an angle iron as a straight edge against the pulleys. Going back to that first picture I showed, had to be a pretty good piece of angle iron. Replaced the air filter. We had spares on site, and so the blower was actually restarted the same day it was discovered. However, they go another 2 weeks, it burns up again. After they had retensioned it, realigned it, and this time the residue there you can see is from a fire extinguisher. Because when they seen it this time, there was actually coal embers, as they could see through the belt screen cover, and they didn't want any wind blowing anything out. So abundance of caution, he just squirted it with the fire extinguisher and powdered it up a little bit. So now we go, what in the world? We got twice in a row, 2 weeks in a row, and this was like we handed the key to $1 million Porsche, and the cylinder ain't running or something. And so as a vendor who supplied all this, we turnkeyed the entire job, the construction and everything of it was done under Triple Points umbrella. I said, well, I'm going to get the manufacturer out there, and we're going to see why is this happening? Is there something wrong where the blower's locking up and the belts are spinning, creating this heat? We want to investigate this. This is just another picture of how much the insulation melted off. So we get the universal blower packs field technician Mark come out to investigate this thing, all angles, all sides. After the second fire, we confirmed a free spin blower and motor, no paint bubbling on the blower, which is an indicator of extreme heat, no material damage. Melted insulation is nasty, and the fire extinguisher is nasty, but it's somewhat superficial. It's just dirty to work around, but the main components are sealed, the blower itself, and so we had to clean it up a little bit, and it didn't impede the operation of it if the integrity of the blower and the motor were okay, and they turned out to be so. But what we determined was the issue is when we're putting these belts on, the distance between these sheaves is rather difficult for one guy and a piece of angle iron in order to see all 4 points. If you put a string across these sheaves, you have 4 touch points on either side of either pulley. And you've got to loosen the motor mounts back here on either side, and then there's big bolts underneath that drive. So if you might tighten one side a little bit, then you got to tighten the other side, and you got to keep checking it. And we probably checked this thing 3 dozen times. And I learned a few things there on these 8 belt drive bigger units. He likes to put on 2 belts at a time and roll them over. Some guys like to put a bunch on and don't loosen it up quite as much as it's loose right here, and just trying to force them to the back and hurry up and get the job done. And care needs to be taken to not cut the belts and get all 8 loaded on there. So in intentioning, there's literally a tool out there that we put a little felt mark on this that's according to the manual of the amount of foot-pounds pressure, and then you simply push up on this until the felt marker aligns with the belt right behind it, and that gets you to your proper tensioning. Now, a lot of guys will simply tighten this and they'll push it and make a determination that's good, and frankly, that's probably okay in a lot of times. But one thing I personally learned on this, when you have 8, your alignment, if you're off just a touch on the inside, the farthest belt away is worse off. And so the string testing, which I don't have a good picture of that here, I'll show a couple of images of it, was incredibly important to continue to make sure when we got this tension just right that we didn't change something with regards to the angularity of the sheaves matching up against each other. And here's just a dramatic version of it. Here's what I drew, this little string right here, and that's just you've got 4 touch points on either side of these sheaves, and when you have space like that, you're not in a good situation. This is a better one with the string right here, because when we did at least 3 dozen string tests, if not more there, you can pull that tight and you can push with your finger against any of these 4 touch points either side of the sheave, and you can see a minuscule amount of space, or the string will give way visually to your eye, which may be kind of hard to see if you've got a pretty heavy piece of angle to be stiff enough to run the distance that we were running. And that's what a lot of sites do, and in this instance it wasn't good enough. It's got to be a lot more accurate. That you can even get into laser alignment tools, but the string is pretty good if you're very religious about it and check it and do it. And so since that date, we solved the problem when we were there and aligned it very, very precisely. And just a note on air filters there, because this site was a fresh construction, there's a lot of riprap. This is only 30 days on this filter. And one time before we had the fire, or after the fire, I should say, the site called, so they had a 20 amp differential between 2 identical motors running full at 60 hertz. And we go, well, that doesn't make much sense. And that was actually on a previous visit to this one. And we found it was just the one filter was really plugged up. And so we take the filter out and put a new one in, and then we could get the amperage down to plus or minus 3 amps. So in this instance, there are 169 amps here, and this is a 225 amp nameplate, but we're only drawing, because of the depth of the Lagoon, we've over designed it a little bit. We're only drawing about 169, 170 amps, 171 amps here. So a modest amount of difference between 2 identical units running is in the norm, but if you're starting to get 5 and 10 and 20, there's something causing that. It's a drag. In this instance, it was a drag of the air trying to come through a dirty filter. So in the end, while I had the guy out there, we did check the second blower, and it needed no adjustment. But the first blower, it got there. When I say the second blower, it was actually the first one that arrived, and it was fine the entire time. But it was the second one that arrived that somehow it didn't arrive. And the manual does say to check these, even after they put it together at the factory and line it all up, to check it before you fire it up. And that didn't happen here. So moving right on to another topic. This happens to be the same site, and I wanted to cover a little section here about how do we maintain pressure when this is a 3-to-1 slope over here, which isn't visually correct in this drawing, but it is a 3-to-1 slope. At the bottom is a 2% slope clear to the middle. And so how that manifests when you look live at the site is this. So this the bottom of this lagoon, you can see where this is just runoff and melt. It's starting to pile up in the middle. So you have about an 18-inch deeper portion right down this middle versus the toe of the slope. So here's your 3-to-1 slope. Here's your toe just right where it meets this 2% slope. And so how do you maintain pressure? This is the early start of the construction at this site. Again, this is sugar beet processor in Idaho. And I'm going to go through why this lateral's on the bottom. Well, I'll tell you right now why the lateral's on the bottom. The site wanted to raise and lower the volume like every 4 months. And so floating laterals on the surface are going to have to go up and down and undulate and bend and potentially crack. So we come up with the design that the site agreed with of putting concrete blocks. And these concrete blocks, I'll have some close-up pictures of them, are actually lined with old liner material. This was completely relined, had to contour some of the, we weren't involved in the relining and the contouring, but everything after that, Triple Point took over and turnkeyed it. So what we want, here's another view of the depth of what it is on the shore or closer to the shore versus out in the middle, you're under the water. So what they like to be able to send this high COD water out there and get the air on as fast as possible. So they've only got maybe 3 feet of water or 2.5 feet of water out in the middle just over these tubes, and they can turn, you can see these tubes are still sticking up, and they're about 30 inches tall, and they've got air going. And this one can be turned on as well. It's just a picture that was taken at a point in time. So one of the things that we went back there after the fire and after, I think we went back after the first 4 months and to look at a drawdown, and we found an anomaly. It was ironically, there's 152 aerators in here, and this is what they look like close up. And this one looked weak, and the site and the operator were saying, I think we got a bad aerator over there. And so we got to look, and we found some previous pictures that we didn't pay attention to until later, but there was a low spot in when the contractor was putting in doing the dirt work and putting in the liner. And so you can see right here that these diffusers are underwater at this drawdown, and even there's a block that's right back in here that's actually out of sight. And so even though this wasn't in our scope, when we were there and got down in the basin, did a walkthrough, and we wanted to check everything out after the first fill up and drawdown, we raised this lateral a little bit, and we raised this aerator up a little bit. And it still might have to go up a little bit more, but they were appreciative that we took the effort to equalize the pressure enough, because air wants to go to the highest spot, not the lowest spot. So this was all low, and so it had a very weak diffusion pattern, which is, you want them stronger here because this is where they exit. They pump out from this end, so you don't want a weak one right there. So we just simply cut some wood, sanded the edges, and got this thing up in the air. It was all that amounted to. So this is a little bit of the methodology of getting the air to the bottom. So these side laterals feed these longitudinal laterals, if you will, and these pipes are going to come up the bank and over and back down to the blower that we've seen in an earlier version. This is just, and here's these blocks. Some of these blocks are quite heavy. I mean, some of these are 450 pounds, the blocks to hold. You're holding down the entire system completely loaded with a lot of air, and you don't want anything floating to the top. Just some close-ups, and I'll note here, and it shows up in several of them, these straps are intentionally loose because when we draw it down, this is out in the sun potentially for a week or 2 weeks at a time before they begin to fill it back up. And so these things it's HDP will shift. This is HDP material and it will shift. These are all stainless fittings. You see the blocks wrapped with old liner. And this is just some, we'd use a local contractor just to build a bunch of these blocks down there. Just pictures of that. And some other close-ups of how we come down. And this is all engineered to size. You can see we're tapering at this point. It's always bigger where it starts and it tapers. This 6-inch line, I think, goes to a 4-inch line as it gets down there, and that's all engineered, and we supplied all that and hired a contractor, did all the fusion and everything. But again, maintaining equal pressure throughout a complete tapered basin. And here's where we're getting ready to go up the bank with the final piping. Here's this one was left off because this hasn't been fused shut yet, nor have the nipples been fused on for the takeoffs for the aerators. So they left these nuts off so they could lift this up a little bit. It's not quite that loose. And just another construction view. Here's another view looking across of getting ready to go up the bank over there. Here's a view. This was a wintertime construction. We fired up in January. Again, you can see the taper in the middle. You've got just precipitation runoff melting going out there. Now you're seeing the aerators being connected just by a short piece of hose. We traditionally will put a long section of hose, a tether, and a buoy. So these can be raised to the surface for individual maintenance. In this instance, working with the site, they says, well, we're going to be pulling this up and down. So any maintenance we need to do, we'll just pull it down and do the maintenance. Although there's some discussion that they've got quite an investment in here and they're getting significant treatment out of this, that they might treat this more as a throughput pond. And then they know that we can go back. We've actually quoted them an adder to put longer hose and tethers on here if they wanted it like that. So they have that latitude in the future. And this is just a close-up of now we've got a fused on nipple and hose bar, a short section of hose. This rope is just to lift it down in there. It serves no other purpose. There's no buoy on the end of it. But these aerators, and for that fact, 900 and some of these pieces of concrete, excuse me, were all zip lined in here. The contractor put a piece of equipment on either side in a zip line system, and they did a GPS to set all these blocks because they needed to be pretty exact. And then they just generally put the aerators in position because the diffusers were added on after they were down in the bottom. But it was, and I don't have any pictures of that, no video. We weren't there. We hired them, and so you just need to get them in there. Don't damage anything. Don't damage the liner. And they did a zip line thing, which was pretty cool. And I wish we had some video of that or some stills. So here's another view of the blowers coming up over the top. And this is a valving station that allows the site to taper down the air at the deeper components. So this one I think is wide open. This one's slightly closed. This one's open a little bit. And this one over here is or closed down a little bit. And so there's some visual diffusion pattern equalization from the top. You can stand up here and look down in the field and make an adjustment. And once you have that in position, it's pretty good no matter what the height of the water is. So then the final thing we did on there is an orifice. And so an orifice went in front of every one of these, and they're cut down to, hundreds. And here's an example. This is for another project where we did, here's the takeoff from a floating lateral, ball valve, orifice, closed nipple, and then so on and out. But this is what I want to draw. It's just a glorified washer, if you will, but it's stainless and it maintains that pressure based on distance away from the blower and other factors. And this is what the site finally looked like when you've got it all, when it's filled and you've got all diffusion pattern going. This is where you get a lot of treatment in that pond, and we're reducing 90-some% of the COD load coming into this pond. And that's why they're considering more, this would be a throughput pond to feed out into other ponds. So just, and then here, this is just a kind of a quick interruption in these case study things to talk about mixing levels and air, and I'll just go over this pretty briefly. We all know about facultative is, you know, no air in the ponds or just natural air, wind and humidity. So when we're doing calculations, we use a reaction rate of 0.12. Partial mix will be 2 to 5 standard cubic feet per minute per 1,000 cubic feet of volume. And you get a reaction rate about, we use a reaction rate, everybody does, of 0.28. And if you jump to complete mix, you're almost order of magnitude being 10 times, so it'd be 2.8 if it was exactly order of magnitude. So when you go to partial mix, complete mix, it's a big difference. In complete mix, everything is in suspension. You're moving the whole thing. You don't have solids piling up or anything like that. Everything's moving. And then not well known is the vigorous mixed kinetic, which is approximately 7 to 8 SCFM per 1,000 cubic feet. And we have attached, or engineers that introduced us to it, attached a reaction rate of 0.85. And of course, we're dealing with RAS, and you can add a lot more area. So here's this is a little case study of a job in California, Murphy's, California, and this is what our preliminary drawing looked like, that the site needed to look like when they're done. This is our primary pond. So this is where, in typical taper aeration, you're going to get about 80% of your BOD reduction in this pond, goes into the second pond for final polishing, and it goes to storage and then out. In this instance, this was all land application to a vineyard, took all the water from this plant in Murphy's, but they had to take this pond and dredge it and take it offline for about 4 to 5 months it ended up being. And so we suggested that they take this scope, install it over here, and let this be the new cell 1 temporarily, if they do the following things. You got to be ready to pressure wash all this stuff when you take it out. We can build a header that can be a temporary header that can get reused up here, that's going to be trenched. And the engineers like that, and the general contractor like that, and we were awarded the job, and so that's what we did. Subsequently, we'll show some photos of that. So this pond here, the pond's being rehabbed, is out of sight up here behind, stage back. So we designed this is a CPVC header, which coincidentally is about a 210, 215F tolerance for heat. HDP is about 185. So oftentimes when we come off of a blower, we'll go through dip until we're ductile iron pipe or black pipe, steel pipe, carbon steel, until we reduce temp enough, and then we'll convert to HDPE, which is a lesser expensive material. In this instance, because it was going to be out in the sun and it was above the 200 exit temperature, they used CPVC and then they just repurposed it. So we sized this up so they only had to make like 2 or 3 cuts, pack it up and put it in the ground later. So this is just temporary manifold, ball valves, hosing going out in the pond. It was all reused. Triple Point has a boat here, and we helped them temporarily install this. This is fine bubble only units that are going in here. There's no coarse bubble contribution as the previous aerators we were looking at. So they had a temporary blower, or the existing blower, and they poured a pad, and then one day they went over and they rehooked it up, a new temporary panel, and just run down this above ground header. So this was the way it was for about 4 or 5 months. And here's just installing, or just pulling hose out from the shore and taking it out to a demarcation point, looking at flags on the bank, and then dropping it. The construction coupe was dropping it. And then we said, you gotta just clean them off when you come out. So there's a couple kind of fuzzy pictures, but when we got ready to take them back out, just pressure washed them off and everything was fine. And so this is about 5 months, because if you they're going to sit out in the sun a little bit and you pull it out of a pond, it's going to dry, you're going to foul. These are EPDM membranes. In the previous sugar beet one, we went with the silicone version. We're kind of going towards the silicone pretty much for domestic waste or food processing now, because we've done some testing and they show a really long life. We're getting on the 10 to 15 year range now. And these used to be the 5 to 7 or 7 to 10. So here's just another view of the site where they've now cut that header and they're going to put it in this trench and go back to this permanent pond, which has now been cleaned out and filled back up. So there's just a permanent manifold now coming up it's coming out of the ground. You don't see it all the way down there. And then we also oftentimes will put an extra stub in here in case the site grows. So we've got 4 or 5 or 6 manifolds that has an extra little stub on it where they could get some additional mixing if they want to put another aerator out in the middle. And they've got a little bit of throttle linkage on their blower with the VFD to slightly oversized, so they have room to, if they have a town festival or something, they can actually, pour the coal to it, if you will. And then here's just an overall final view. Here's the new pond that's been rehabbed with all of the diffusion patterns in it, a little bit of final treatment over here, and all this eventually goes to these vineyards over here. There were some of the folks involved in that job. Now I'm talk about a rolling open for a second. What I mean by that is here's Eagle, Idaho. This is 2016 Google. And they wanted to switch over their aeration. They selected Triple Point to put this job in 2017, but they could not afford to be without treatment. They couldn't just take all these big 50 horsepower, I think 25 horsepower, I believe, surface aerators out and just wait to put this all in. They got to kind of just in time. We'll take these first 2 out and let's put in floating laterals and fill them up. And we'll take the next 2 out and put in floating laterals and so on and so forth. So it was a rolling open, unlike the last one where it was just a fell swoop, take the pond offline and put aeration in another one. So here's what they look like in early 2017, these big splashers, and they're 11-foot depth. So these are tough efficiency, and they kind of lost treatment over time. And the maintenance was wanting them to move on to something a little bit less maintenance happy. It's just pictures of taken of the old ones that were taken out. So they couldn't, as they're doing a rolling open, they said, let's go fuse these 180-foot long HDP laterals in an adjacent field. And then we'll drag them over there, and they put a temporary cap on one end and they float them on the pond as like logs going into a log yard that has a pond. And so that's how they were able to stage all this and get the job done, work with the general contractor, working with Triple Point. And now what it looks like is, it's an above ground header. This is a 24-inch header that tapers on down here. Got a flex piece, and these were the pieces that were built off site. These are 190 feet long. And they were drug over, and they've got nipples on them with caps, and some of them to this day are still capped off for future growth. So it was designed at the time at around 1.8 MGD, and it's already up to about 2.2, and they're already working on phase 2, and we're actually involved in that. We've been selected, and that job will be installed in July right now. So here they've got a master valve that shut off the whole line, and they've also got individual ball valves out on the water to shut off individual aerators if they wish. Here's just going in now. Now you have the aerators connected to the laterals, and so these and they specified they wanted 12-inch inflatable buoys to designate where the aerators were. So this is just mid-construction. And then a final overhead view. An interesting thing here, our engineers were modeling this, and we recommended a baffle right here. You can see where these are closer together over here. And so this zone is actually a vigorous mixed zone, and this is a partial mixed zone. And it was CH at the time, which is now Jacobs. They talked to the site and said, look, we can always add the baffle. The site is not a big fan of baffles, just don't put the baffle in. So because of the, it's a 210-foot wide pond total and some 700 feet long, we get a natural zone change right here from a vigorous mixed kinetic to a partial mixed kinetic without a baffle. And it works, and we're ahead of schedule or hitting better than what the design criteria was for BOD out the back. Now these things are just some walkways that had little air sparges on the bottom of them from before, and they wanted to leave them there. They didn't want to deconstruct them, and they wanted to keep the air spargers, and so we said fine. We attached zero value to it because we didn't know what to attach to it, but so they kept them, and they take samples off of them, and they have a service boat actually that they tie up to the side over here for going around for any maintenance they might need to do. So this is just a quick hitter Lagoon tip. I just took an email last week from somebody about breaking up a velocity. So here's what somebody, this happens to be Bishop, California. And they used to come in the corner over here, and the water would just scoot out and start building up walls. And so it's scooshing out the water farther and farther and this is a big, long pond. And so Steve Harris is a consultant, that's him right here in the boat. He recommended to do this, and they did it. And it's basically you're breaking that flow up, you're loading your pond more evenly, and it's kind of a poor man's trick. I mean, this is a goonite line pond, so they did have to do some stuff behind the scenes and get this new point coming in from the corner, but they're relatively inexpensive, and tying this back to split it up and what it did for them, you know, paid great dividends versus the cost that went into it. Just another view of it. Here's a job in Revelstoke, Canada, and this was a 4-alarm odor control call. And it's kind of interesting because Revelstoke is a known ski area for real ski buffs. Revelstoke Mountain, it's got a lot of downhill run, I don't know, some vertical feet that's off the hook. And this Revelstoke city is kind of down in the bottom of some mountains, and it's cool enough up there that people don't really have air conditioning. They open their windows in the evening to let cool air in, and good. And this thing was going septic and going bad, and it hit Facebook. It was an election year. It was every one of these elements, you know, it's this political conundrum. People writing, everybody in the city's driving a brand new truck, and yet you know, trying to barbecue my steak at night and I got to smell this stuff, sort of comments. And the city bought this direct, and they kind of mired around on it, the city manager, for a little bit. And then when they made a decision, they wanted to go now. And I got an email from the city engineer, because I managed this job. I went to help them start it up. That, is there any way you can get this any faster, as fast as possible? And so we said, yeah. And they had all this old stuff in the bottom, and they weren't going to take it out nicely. They just got a great big backhoe, and they had roll-off containers, and they would just brute force it out, cut off saw, pile it up, brute force it out, just drug this stuff out. You see the weights that was tying some of this down out there. And this was their old stuff. There was just no methodology to really lift this, to change it out. And so they just took it all out and cut it all up, and they piled it all up and just put this whole new system in, and it did the job. Matter of fact, they had 3 75 horsepower blowers, 2 of them going all the time, and 1 they would turn on occasionally. And with the new efficient system, they were able to go back to 1 blower, and they were seeing significant savings in their utility cost day 1 from that thing, and the odor complaints dried up. Here's another little job. It's nice, it's fun to work on these great big jobs like the Sugar Beet, Eagle, Idaho. Those are big, large jobs, but some of the jobs I remember going to were, you know, it was between me and an owner and Ace Hardware. He built his own little header. And we supplied, from the ball valve out, this little 3 or 5 horsepower blower that put in, and he had to stick in a power. So this guy employed like over 150 Navajos. He had almost a little city of his own. He was just quite the entrepreneur. He had car lots, tax preparation, grocery store, convenience store, credit union. I mean, he had all this stuff, and he was his own operator and his own private ponds, and they were just a evaporative pond and 2 sets of ponds, and they actually go to a wetland if he started to fill them up. And so there was no ratepayer he's going to. It was going to be his money out of his pocket. So this is one of these sub $20,000 jobs that I did. That was kind of one of my favorite jobs, because all my helpers were Navajo guys that worked for him. And he had no way to get the aerators out in the middle. This is the final view. It's just 4 small little fine bubble aerators. He only had 3.5 feet of water. He's trying to get it up to 5. And he was a terrible color and starting to smell, and we got him turned around pretty quickly. But it's kind of a interesting job, because one of the Navajo guys, we had no way to navigate, no motor on this boat that he had. So they tied a rope on the back of a pickup and strung it to a pickup on this side. And then the boat's too wiggly. You can't get 150 pounds with the aerator up in the boat. So I said, well, build some sort of a little raft. So he got a little blow up raft, kids raft, and some swimming pool noodles, taped it together. So I rode in the back of the boat, drug the aerator. We got the aerator loaded up on this, which would half sink, which was fine, and drug the hose out and got it out the demarcation point. And it's just kind of a fun job. You just do what you do in your small town USA and what resources you have, and I'll just not forget that job none too soon. Now this is an interesting one. It's still like this. This is in Washington State, and this is the liner is lifted. It's lifted back here. It's lifted here. I don't have no whiz-bang solution on this other than they've shut off their surface aerators. They have a discharge to this creek, and it's been like 3 years now, and they've got an engineer for this, but they're unsure what to do. The most recent thing that they were talking about doing was weighting this down and forcing it back down. What some of the theories are is they might have been built over some old swampland that's emitted gas, that's lifted these up. They don't want another one to come up and get in the bottom of a propeller over here. But this is a pretty good landmass, almost, and it's still like that. I drove by it 2 weeks ago, and it's still got this big hump in the middle of it. And I've been going to call Devin and say, you guys got a plan for that or what? Because they have a phosphorus. They're going to a sensitive creek over here, but I think the Department of Ecology's get them a workaround for now. But I don't know the update on this, but maybe I'll get it by next time and see if I can find out what their plan is. Here's another small one that they did, another one of these small sub $20,000 jobs. These guys' pond just went to heck. McClure Boat Club was a bunch of homes on a lake in California, and had their own little lagoon system, and amongst themselves they were their own operators, and they had algae, duckweed is getting to be in tough shape, and just no oxygen. It was just an old facultative pond, an evaporative pond too. Let's see if I can forward this. And then, we go up there and put a couple little fine bubble, little 3 horsepower blower, little manifold, little gauge, some hoses out there, and we just get them turned around real quick. And that's not triple point or anything, that's just putting some oxygen in some dead body of water. I mean, it's just helps things out tremendously. To that point, I wanted to just talk about this for a second, because we have continually seen, we're getting studies built up now with data of sludge reduction when you put in diffused air in the bottom of a pond. And so this is some information from, this slide was basically stolen from Steve Harris. I should put him credit down here somewhere. Actually, I rebuilt the slide from information from him, but and I've done these tests several times. I've pulled samples at Scheid Vineyards in Central Coast, California, and other municipal places, and says, let's go run a volatile solids and a total solids. And if the volatile solids comes back, it's going to tell you basically what all this is volatile solids. And he's saying right about 85% of dead bacteria. And in the tests I did with wineries and stuff, I was getting 70, 71, 75 with lab tests. What that tells you is that solid sitting on the bottom is a lot of that's available to be further reduced, oxidized, chewed up, if you will. Now, if it's grit and sand, you know, nothing's going to do anything for that. That's going to have to come out. The balance of that implied, you know, the 15% is going to be grit and sand and, you know, air deposition of things that just aren't going to be bioavailable. And so when you appreciate that and you put the fine bubble diffused air right down in the middle of that, you know, you're gonna, and I tell these guys that we're gonna foam, because a lot of times they'll have the solids cleaned out, but sometimes it's not. We're going to go right down into some muckety muck. And I said, I'm going to tell you, we're going to foam, because there's some reactions that happen immediately when the surface of the fine bubble contacts down there. There is a charge and some things happen quickly, but you also are getting your biomass going, and foaming is simply off-gassing. You're getting CO2, nitrogen gas, and that sort of thing. Here was a winery in Idaho that was 24 hours after startup, and it was actually an evaporative pond. And so you've got foam coming over here to the bank. It's actually getting pretty thick. It was pushing up here, but till this acclimated. So you can go 4 to 6 weeks, and you know, is what I tell operators, to acclimate, and then it kind of settles down when you're adding air to something new that doesn't have air before. So I'm a little bit short. I got a couple bonus slides I'll go to, but there is a question section that you can post some questions in there if you've worked up anything. I'm going to go on and cover a couple of these bonus slides. This bonus slide is kind of funny. It's not really funny. It's circa turn of the century. I think it was 30s we looked up. And what this is a mining area. It's kind of a washed out photo. And these homes have their separate outhouse, and it was considered, you know, quite a conveyance system of the day to come out and have your own private commode that goes right over this water body and just carries the waste away. It was like, we're thinking, good, we don't have to deal with that. Let's get it out of here. And there's some mindset, I think, that still is like that to this day, but quite an interesting old photo from around the 30s in a mining area. And just want to talk about for a second, it's like this thing kind of got squashed longwise, but bubble size. When you talk fine bubble out there, pretty much accepted that a fine bubble is between 1/8 and 1/4 inch. And a coarse bubble is on the order of 4 to 6 inches, so it's pretty good sized. If you look at a 12-inch bubble over on the left here, the surface area, that's 4.8 square feet. If you cut that down to a 6-inch bubble, you got 185 square feet. Now what happens when you release a 6-inch bubble 9 inches off the floor of the bottom, which triple point system does? You get a lot of mixing. That's tumultuous. That wants to get up to the surface. Just like this one would want to get up to the surface if we were doing 12-inch bubbles. But the problem with that, you'd create little activity alongside, but you'd off-gas quite a bit of it, so you lose efficiency there. Where you really get efficiencies, you go back to the same volume and you go down to, and this is just a representative concept. You go to a fine bubble, which is your 1/8 to 1/4, you got all kinds of square feet. This is where you get oxygen transfer. Mixing, oxygen transfer, which is the EPA definition of aeration, mixing and oxygen transfer. So bringing a lot to the party there. The other thing is through Brownian movement, your fine bubbles are going to want to hang out longer in the continuum, in the strata of the depth of the pond. And this is an interesting site that kind of take into multiple concepts here with regard to the solids. First of all, this is a high elevation, and they wanted all this manifold system under buried because they had these snowbergs that come through and just push fences over, and they call them snowbergs. And so we agreed to design the system so it was underground like this, and the hoses just come out down the bank and go out. Now they wanted longer hoses because they did a sludge profile. This has an old wooden baffle. Actually, and it was rebuilt as a wooden baffle on the rebuild here in 2018. And they wanted these hoses longer because they knew sections, and this is actually a big rock poking up in the middle of this high mountain natural kind of reservoir here, but carved out somewhat. To move the aerators around later to put it where the solids were, back to that volatile suspended solids component, and reduce solids that way versus having to hire a contractor to come in and reduce the solids, because they had a pretty good profile. They knew where they had some problems. Statements corners oftentimes are solids prone buildup. And so they were taking advantage of that. And Jeff they've went out and they've got their own little boat, and they went out and moved, and they've got a number of aerators on the other side. They've got, I think, a dozen over here and 4 on this side of this pond. So they're still getting value out of that, getting solids reduction as time goes by moving aerators around. So I've ended up a little bit ahead of time here, and if you have any questions, I'd be glad to address that. It's also being recorded. If anybody wanted to look at it again, it'd be available. So question, baffle materials you have seen. Well, until I seen this wooden one right here, I actually had seen some wooden ones before. It's literally 2x6s between poles that are driven, pile drivings that are driven in the ground, but mostly HDP material for baffles. We supply baffles in some instances, and oftentimes we'll go across a body like this, and we'll have a window at one end strategically because we want the water. In this instance, they would have the window. We put the window at the far end because the water comes up stage right and goes into it, and you want to force it to go its longest circuitous path to take advantage of full HRT, hydraulic resonance time, for treatment. So HDPE, and in a location like this, they actually went back with wood. But then again, it is interesting, back to that Eagle Sur district, that very long, 700-foot-ish long by 200-ish foot wide. We got a natural migration of different zones from vigorous to partial mix with no baffle, just by the passage of time. I mean, just by the sheer distance. And so that I'm actually a couple other deals like that where our engineers are saying we should put a baffle in to create the zone. And these are in Oregon. These ponds are so large. We are telling the engineer that we're dealing with for the client that our modeling says we should put a baffle in, but we think that you will naturally migrate to the next zone, and it'll save everybody money up front if we don't put that baffle in. But we collaborate with them on making that call, whether or not we put a baffle in. So here's another question. How well or how do you maintain an aerated pond system when we normally have up to 40 inches of ice coverage for over 3 months of the year? Physics will say that a diffusion pattern will not freeze to 50 below zero. So pond will ice over. We have some cool photos of one where it was 20 below in Iowa. And the diffusion patterns, there are nice round patterns out there that are still open, but everything, you could walk almost right up to them because the ice is thick. If it's incredibly cold, 40 inches of ice is, I guess we wouldn't be adding air when there's already 4 inches of ice. It would be my supposition that if we had aeration going in the bottom of the pond, that the above the diffusion pattern would not freeze 250 below. And Eve, if you're monitoring, I don't see any other questions unless I missed something. Okay, that looks like that's a wrap. No more questions, and thank you for your attendance, and we'll see you on the trail.